Take it away. Alrighty, good morning. I'm Steve Horejsi, KE0VDC. I live way down yonder in Rosemount. I have been in this hobby now for 5, 6, 7 years, something like that. I'm a bit of a technology junkie. It seems I never met a tangent I didn't like, so I wander off and find all kinds of other things, and this is one of them. And this has been a fascinating journey for me, so I thought I'd share this. We're going to talk today about 3D printing in general, and let's see. Well, that'll work. There we go. Okay, so the questions are, first of all, how does this relate to ham radio? What's this got to do with anything? And what kinds of things can I make? What exactly is 3D printing? And I want to go through some example projects. And then I want to talk about materials you can print with, because there's always questions about, well, what's the plastic like? Well, there's dozens and hundreds of kinds of different stuff, and we'll talk a little bit about different materials for different applications and why you would choose one over the other. I have a section here labeled Exotica. There's some really leading edge stuff happening in 3D printing lately. There's people printing glass, there's people printing metal, there's people printing ceramics. And so that's not necessarily something you easily do, but it's within the realm of this whole 3D printing thing. We'll have some time for question and answer, I hope. I had a lot of material. I was originally thinking that we would make this like a 2-session thing back to back, but two problems. First of all, they didn't have an extra time slot, and second of all, nobody wants to sit through 2 hours of this. So what we do have is the room kind of across the hall over that way that was used for VE testing. That's open, and we have access to that after this. So I've got some stuff I brought along if you want to come over and look at what some of this stuff looks like and ask other questions or just chat about things. That's where we'll be. It's like it's room 140, but it says VE testing all over it, so it should be easy to find. So first of all, how does it relate to ham radio? Well, first of all, it's all about fabrication. Ham radio operators have always been builders. Could be homebrew rigs, it's antennas, it's station stuff, it's mobile installations or project packaging in general. And these projects have always required fabrication skills like metalworking or woodworking or finishing or drilling or grinding and that sort of stuff. And sometimes this became an obstacle, particularly for myself. I am not what you would describe as a workshop superhero. I don't know how to do a lot of that stuff. So consequently, when this came along, it was an option for me to be able to build things, and I wasn't limited by my fabrication skills as much as my design skills or my imagination. And it's opened up a lot of avenues for me, and I really do enjoy it. And like I said, no caper tights required. This stuff is pretty easy. This is not rocket science. If I start out with what I can make, the first thing I want to talk about is just plain old enclosures. We're always buying these little metal or plastic boxes to put projects in and stuff like that. And this is my first plug of the day. Is this thing? This thing is from a online neighborhood called Thingiverse, and it's basically called a Universal Project Box. Oh, it didn't advance. There it goes. And I really like this thing because first of all, it comes in about 7 or 8 different sizes. You can just download it and print it if you want. It also comes with all the CAD files. So if you have a CAD package, you can stick this thing in there and customize it, put in all the holes you want, standoffs, reinforcements, whatever you want, partitions, and then you can print something that's ready to roll and build your project around it. And you can end up with some pretty nice stuff because of that. I actually have a example of this that I can show later. Next thing, simple things like knobs and buttons and levers and switches and stuff like that. If any of you have ever repaired any Heathkit stuff, you'll recognize the one on the upper right. Those things break. They're hard to find. You don't have to scrounge around Hamfest now for them. You can just make one. Make as many as you want. The knobs on the upper left are Heathkit knobs as well, and the designs are available. You need a knob, print a knob. And if it's a new design, you can pick one that you like and print exactly the size and shape you want, use the plastic and color you want. It's very handy to be able to just do that. Some other examples, antenna parts are real common 3D print things. Element clips for Yagis and stuff. There's dozens and dozens of designs of those available, both for handheld and VHF, UHF verticals or horizontals and Yagis. And coil forms for loading coils for portable antennas, or just coils for general projects. Center and end insulators, if you need an insulator of a particular specification or design, fine, just go ahead and print one. You can do chokes, balanced trap enclosures. There's some of these designs that are center insulators for a dipole and include a waterproof box. You can put your handmade balun in and keep it out of the weather. So it's all in one piece. You print it. Some other things are brackets, couplings, protective handles, a lot of go box stuff. I see a lot of guys that will print basically a panel for a go box that has custom openings for their particular equipment and the accessories they want. They can mount it all in there cleanly. It's not a kludge or a hodgepodge. Some of them even print the whole box. I mean, you can do kind of whatever you want. So there's a lot of that kind of stuff. And then there's the what I call the just stuff category. You know, rope tighteners for field day. There's a lot of key paddle designs. People get to design their own paddles and decide what shape they want, what size they want, what spring tension they want, if they want a particular shape or clearance from the desk, whatever. A lot of these winders for portable antennas and stuff like that, for portable things. Just something as simple as a call sign display or a microphone bracket or a panel for power distribution, or all these kinds of things that they're just very, very easy to do. The next question people are going to be asked is basically, where do I get the design files? Where do I get how do I figure out how to do this? Well, there's a bunch of sites available. I use Thingiverse a lot. I use Yegi a lot, and I do use MakerWorld a little bit. All the others, there's a lot of overlap. Last number I saw, right now Thingiverse has just a shade over 5.3 million files available. There's likely to be something there in the category you're looking for, and many of them not only are the design file for the object itself, many of them include the CAD files, so you can modify them or customize them if you want, and get exactly what you want. And there's always design your own. It's not as hard as it sounds. I happen to use Fusion 360. I know there's a free version of SolidWorks available. FreeCAD, TinkerCAD, SelfCAD, OpenSCAD. Those are all open source, freely available tools. There's a little bit of a learning curve. It's not too bad. I learned Fusion 360, and it probably took me about 3 or 4 days to get comfortable with how it works and what it does. And I do have one piece of advice there, and that is take the time to learn the tool before you really dig into your first design. And the reason for that is you can get the tool to do the work for you rather than it's you struggling trying to make it do what you want it to do. So if you learn the tool first, and it's really not a huge learning curve. I'm going to talk a little bit about exactly what is 3D printing. So we're going to talk about some terminology here, because you hear these things all the time, and it's like, what does that mean? So 3D printing is part of the whole realm of ADM, or additive deposition manufacturing. And what that really means is you're building things by adding material as opposed to subtracting material, as it would be in you know, basically a machining or CNC kind of environment where you're removing material to expose what you want. You're adding material and building from the ground up. There is a subcategory under that called fusion deposition manufacturing, and that's where you're using heat to fuse material, and that's exactly what we're doing when we're doing 3D printing. We're melting a plastic material and we're depositing it where we want it. And The 3D printing I want to talk about today is an FDM process. I should mention that there is another type of 3D printing called DLP, or digital light processing, and that has to do with a photoreactive resin. And basically it's a resin that solidifies when exposed to UV, and so basically they use either an LCD or a laser to write their design on the surface and then draw it up out of the tank of resin. That produces extremely fine detail. If you're doing things like miniatures for a model railroad layout or something, that's probably your technology, because it can get extremely detailed. It might not be what you want from an amateur radio perspective, from the standpoint that the parts are generally not structural. They tend to be rather brittle. But if you're not going to use them to support weight or support a strain, they're perfectly fine.
They tend to be more expensive?
That's a good question. I don't really know. I don't think it's radically more expensive. I think there are limits on size. In other words, you can print some rather large things, probably larger than you can do with a DLP setup. But I don't think there's a huge difference in cost. So the first thing I want to talk about is when you print, people talk about filament. Well, filament is the raw material you're printing from. It looks like a giant reel of spaghetti. It's about the diameter of it. It comes in a big paper or plastic reel. As a matter of fact, it looks enough like spaghetti that one of the popular suppliers is named Protopasta. It looks like spaghetti. The materials melt somewhere between 190 centigrade and 300 centigrade, somewhere in that range. The most common filament diameter for hobbyist printers is 1.75 millimeters. That's about the size of spaghetti. And the standard reel is a kilogram, 2.2 pounds, and it contains about 335 meters. And yes, almost everything in 3D printing is metric. So you're not going to hear inches and cubits and anything like that. It's going to be all millimeters and centimeters and stuff. It's not that hard to get used to. Let's see, then we're going to talk about the hot end. The hot end is the actual mechanical piece that melts the plastic and lays it down where you're printing. And the hot end is actually more complex than just a little piece of plastic or piece of metal that the filament goes through. There are several parts to it. There's the heater, the nozzle itself. There's a thing called a heat break and a heat sink, and typically a fan. And the whole goal is to keep the filament below its melting point until it actually reaches a nozzle. If the heat creeps back up through that assembly and melts things, you get just a spectacular clog. They're really difficult to clear. Consequently, you want it to stay cool until the last second when you melt it. The heat break is often made out of titanium or stainless steel, and you would ask why. Well, titanium and stainless steel happen to be very poor conductors of heat. And so consequently, the nozzle can stay hot and the tube can stay cool. So if you ever wondered why stainless steel cookware sometimes has a copper-clad bottom, there you go. Stainless steel is not a very good conductor of heat. Here would be a good cutaway view I found of a typical hot end. And you'll see the nozzle at the bottom surrounded by the heater. The heat break is the tube that connects it to the feed tube up above. There's a heat sink there. There's a fan cooling it. This is every 3D printer has one of these, and that's very much like what they look like. They are not that big. I mean, the whole hot end is easily fit in the palm of your hand. The hot end temperature can run on some printers up to 350 C at the bottom, and yet it stays cool enough at the top that the filament doesn't melt and clog. You'll hear people talk about an extruder. Well, the extruder is the thing that actually feeds and pushes the plastic down through the nozzle or hot end. And all it really is typically is, it can be pinch rollers, but it's usually just a little pair of gears that grab the filament and push it down and control the rate of feed. Some more terminology. If the extruder is mechanically part of the hot end, they call that direct extrusion because the extruder is right there with the hot end. There's also, and it was more common in older printers, where the extruder is separate, and then there's a Teflon tube from the extruder to the hot end. They call that a Bowden tube, and that's called a Bowden tube printer, by the way, if you have that design. Bowden tube is a gentleman by the name of Bowden who back in the 1800s invented a flexible cable that went through a lubricating sheath. It's like what runs the throttle on your lawnmower or snowmobile or whatever. So if you take a Bowden cable and remove the cable, you've got a Bowden tube. That's exactly what it is. It's just a flexible lubricated tube that we push the filament through. People get hung up on that term and wonder where that came from. And then there's the print bed. That's where the piece actually gets printed. It's motor driven by position. Most beds actually are magnetic. We'll talk about why in a second. There's two different general designs. The older design was that the bed moved in the Y direction, and the head moved in both the X and the Z dimension. And that was a design that's euphemistically referred to as a bed slinger, because the bed moves around a lot and the part goes for quite a ride during the printing process. It gets moved around a lot. The more common current design is the bed moves in the Z direction only and the head moves in the X and Y, and then for some reason they call that core XY. But anyway, that's the general design of the printer, and so you'll hear that term too. The bed is usually heated, and two reasons: better adhesion of the parts you're printing, and it reduces part warping because it slows the cooling process of the plastic. The plastic is going from very hot to very cool, and it shrinks, of course, as it does so, and there are stresses, and if you don't relieve the stresses, you end up printing a banana boat. It curls up on you and becomes a problem, something not useful. And yeah, the bed is usually heated somewhere between 50 and 120 centigrade, something like that. It's a common range of capability. And then there's the actual print surface, the place where the part actually lands. It's most often spring steel, and that's so it sticks to the magnetic bed and stays put, and then you can peel it off and flex it if you need to get the part off, or to replace it with another bed if you want a different print surface. It's typically coated with a plastic called PEI, polyetheramide. That aids in both adhesion and subsequent release. Obviously, you want the part to stick while you're printing it. That's really important. You also want to be able to get it off when you're done. And so PEI and the spring steel combine in such a way that when everything cools down, everything contracts. Well, the plastic contracts more than the steel. And if you let it cool all the way down, it will generally self-release. It'll just pop loose by itself because of differences in dimension. So it makes life a lot easier. Some things, this was probably true earlier on, although it's still used today. They print on glass. They print on borosilicate glass or Pyrex, and then that requires an adhesive. And that has the advantage that the plate is very, very smooth and very shiny. If you want a very smooth finish on the part you're printing, you can print on glass, and it turns out very, very nice. You need an adhesive when you do that, and there are a bunch of high-tech adhesives specifically for that. Some materials just behave a whole lot better on glass than they do on PEI. And then there's potentially an enclosure around this whole thing. It's sort of optional. Most of the newer printers do have an enclosed print space. The enclosure might be passively or actively heated. Some of the higher-end engineering plastics need a heated space so that they, again, cool down much more slowly and relieves the stresses so they don't warp or crack. And often include a fan and a filter, because some of these plastics do give off unpleasant things when they melt, and you want to be able to filter that out or exhaust it out the window even better. So that's kind of the thing that you'll see or hope to see. The last little piece in all of this is a CAD package. If you're actually going to create your own stuff, you're going to need some way of doing it. If you're not going to do custom designs, you can get away without it if you're just going to download designs off off Thingiverse or the internet or something and print them. You don't necessarily need a CAD package. But if you want to do custom designs or you want to customize things that you find there, you will need one. There's a bunch of different packages available. All accomplish more or less the same thing. Some are graphical in nature and some are what are called parametric or programmatic. Graphical things, you grab primitive shapes like circles and squares and rectangles and lines, and you manipulate them and dimension them and extrude them and build what piece you want to build. The parametric ones are more like programs. You define things that say, I want a sphere this size at this location, and then I want to repeat it 6 times over this way, and that sort of thing. And if you prefer to do this programmatically, there's ways to do that. Some CAD programs accept both. So your choice again as to what you want to do. The resulting object then is usually it's a 3D mesh. It's a mesh of interconnected triangles is how they model 3D objects. The most common format is STL or stereolithography. If you see a file, it's have a .stl extension. That's what it is. A typical print for a moderately complex part might have anywhere from 50 to 100,000 triangles in it of various dimensions all stacked together that builds the piece. And you'll notice sometimes when you print, if you print something round and look at it, you'll notice it actually is faceted around the outside. It isn't really round, but it's a darn good approximation of round. And that's just a matter of how these programs work. There's also a thing in here called a slicer as a piece of software where you have this stereolithographic model, a 3D object. That's not the way it's printed. It's printed in thin layers, one after the other over the top. And so the purpose of the slicer is exactly what it sounds like. It's to convert this object into a stack of slices, each slice the thickness of one print. And then they're printed subsequently one on top of the other until you get the object that you really want. Besides the basic mechanics of slicing the design, it takes into consideration things like line width and line thickness so that it knows how thick the slice should be and how many passes you need to make to build the thing you want. There's things called wall and fill. 3D objects are generally printed with a perimeter wall, and then the inside is filled in with, crosshatch lines or something like that. Because concentric circles kind of get in trouble when you get small. So they basically fill with a geometric pattern. The fill can be 100%, meaning it's all solid plastic on every layer. It can be somewhat less than that. Many parts, you need the wall for strength, and that's sufficient, and then the fill is just there to support the wall, and it makes the part lighter and faster to print and cheaper. So you'll see infill numbers that are 30, 40, 50%, and it makes the part a little more reasonable. A little bit more about the slicer. It also manages some of the material settings, like the nozzle temperature, bed temperature, chamber temperature, print speeds, how fast you're extruding the filament, how much you're laying down. All of that stuff goes into the code that's getting emitted out of the slicer, and it comes out as something called G-code. And G-code was used in the old CNC machines in the 60s and 70s. So it's been around a long, long time. They just took the G-code format and they added some additional opcodes to it to handle things like position and extrusion temperature and speed and those kinds of things that were not part of the old CNC world. And then the G-code is what actually goes to the printer and drives the actual print process. So here's a kind of a thumbnail view of how it all fits together. You have the CAD package or your download site. You get your design. You produce an STL file, or you download an STL file. It goes through the slicer. The slicer takes in the parameters like I'm using this plastic. I want it at this temperature. I want this thick of a layer. I want the walls this thick, the infill like this, whatever. It It turns that into a piece of G-code, which gets downloaded to the printer. I've picked a printer off the internet and put some arrows to kind of show you what it looks like and how it all fits together. And G-code would be, I've seen G-code files anywhere from probably 1 or 2 megabytes up to just a shade over a gigabyte for a large object. So it's pretty detailed stuff. It includes each individual step that the stepper motors will make in moving the part along. So and that will be machine specific as well as material specific. So it's not like you can just download a piece of G-code and stick it in your printer and print it. Probably won't work, right? Some example projects. So here's the problem statement. I bought a portable mast for field day, and I bought a tripod to go with it. The outside diameter of the mast is about 35 millimeters. The inside diameter of the tripod rings is more like 50, so it kind of rattles around in there. So I thought, well, I'll print a bushing. So the bottom left is the rendering out of the CAD program. It says that's what it's going to look like when you're done. The middle one is the actual printed part, and the one on the right is installed in my tripod. It worked out great. Nothing to it. I don't know where you would have gone to buy something like that, but it was very easy to make. Next thing, okay, so now the mast is stable, but the mast does not have any attachment points for guy ropes. So consequently, again, on the left are the things that I modeled as rendered by the CAD program. It says they're going to look like that when they're done. The bottom center is what they actually did look like after I printed them. Somewhat to the right, you see the mast with the installed attachment points. And on the far right is the mast actually erected at field day. And yes, I know it's not perfectly straight, but it was field day. It worked very well, by the way. It gave me a very nice way to anchor the mast and have it stand up and work. So very happy with how that turned out. One more problem statement. My inverter generator does produce some line noise, and so I needed a line filter. And this is field day. KB0NES, a member of our particular club, is noted for saying that field day is always held on the third rainy weekend in June. And this year was no exception. It rained several times. And so basically on the bottom left is a box that I designed. I started with that Universal Project box design that I put the plug in before. Took it in the CAD program. I put some reinforcing bosses where the openings were going to be. I put standoffs in there for the actual EMI filter element, and where the stud was going to go out the side for the ground lug. And on the right is what it actually looks like. And you'll notice a couple of things. The entry and exit of the extension cord is through some electrical gland fittings. They're nylon, and they're 1/2-inch NPT pipe fitting. So I just threaded the box and threaded them right in, and didn't have to put any nuts on the inside. And I also printed, as you can see above by the lid, I printed a gasket. I used a more flexible filament to print myself a nice little gasket to put under there. And sure enough, after laying out in the rain, unprotected, laying out in the rain for the whole weekend, open it up and it's completely dry inside. So it actually worked out really, really well. Didn't take me very long to print. I have a very durable, reusable design now. And had I tried to do that from buying a plastic box and doing it myself, it would not have looked nearly as nice. Yes, that actually turns out to be really easy to do. You print an opening, and you purchase these little brass inserts, and there's a tool that fits on the end of your soldering iron, and you stick them right in there. And then that way you can take the lid on and off without ripping the threads out of the plastic. Plastic threads are pretty much single use. You can thread something and it'll hold, but you start taking it apart, it's not going to last. So I use the brass inserts a lot. I also use them under the mounts for the EMI filter, although I probably will never take that out. The other thing you can't see is, besides using the plastic I use for the gasket is called TPU, which is a flexible plastic. I also printed some TPU washers that go around the ground lug on the inside and the outside to seal that connection as well. So everything ended up watertight, and it's actually pretty easy to put together. So, problem statement. I got all these little plastic boxes full of parts, and they're nicely labeled, but they're all kind of stacked in heaps and stacks and piles, and you bump them and they fall over, and it's hard to dig through them and find what you want. And so I decided, well, I got these little 6 by 12 pieces of 1/8-inch birch plywood, a little stack of sheets, and I thought, those would make really cool shelves for little parts. I need a shelving unit to put them in. So what we end up with is exactly that. Bottom left is the what the CAD program said it was going to look like. Center bottom is what it actually printed like, sitting out on the table on my patio deck. It's 12 by 12. It's roughly 12 inches square and a little over 6 inches deep. And on the right is what it looks like with the shelves installed and the parts placed. And it turned out to be really nice. I like it so much I'm going to print several more of them, actually. I'm going to change the shelf spacing a little bit, but that's easy to do. And that took me about 45 minutes in the CAD program to design that. It took about 25 hours to print. but I did end up with a really nice little plastic shelving unit. So that's part of it. There's one thing that has to be mentioned is the fact that some of these things do take a while to print. They're not like go into the shop and whip it out in 10 minutes. It takes a while. But that's okay. Patience is a virtue, they say. The next thing is, so what about the future? What are some other things that I'm looking at? Well, this one captured my attention. And it is on Thingiverse. And it uses either a spindle motor or a Dremel tool. And it's a CNC-driven router. And so everything in blue there is printed plastic, and I have printed all of the parts at this point. I have secured sources for and purchased all the mechanical and electrical parts. I have everything in 2 big boxes, and that's what this winter is going to be about, is putting this thing together and see if we can't get that to work. So maybe next year's presentation is on CNC machining for the radio amateur. I don't know. We'll see. Let's see how well this works out. But it looked fascinating to me, and I really wanted to try it. So we'll see how that goes. Next thing I want to talk about a little bit, I don't want to spend a lot of time on this, is materials in general. What can I print with? Nearly any thermoplastic material can be 3D printed. Some are better than others. Some you probably shouldn't. I want to talk about 8 of them because they're the most common, and there's many, many, many more above and beyond that. This chart was arranged in order of ease of printing, the top being the easiest to print, the bottom being probably the most challenging of the 8. Interestingly, if you were to rearrange this chart in the order of popularity, in terms of how much people use, how much people buy, you'd find it was pretty much the same order. People print the easy stuff, and they tend to shy away from the hard stuff unless they really need to. Also, interestingly, it's approximately price order. So the top items are the least expensive plastics, and the stuff on the bottom is the more expensive. And it just works out that way. I'll go through these fairly quickly just because. The first and most common is PLA, polylactic acid. It is actually a bioplastic. It's made from either cornstarch or sugarcane, and it is renewable. It is not necessarily biodegradable because of the process it goes through. It's inexpensive, easy to print, durable, very high tensile strength. It's fairly rigid. When it prints, it gives off a faint odor somewhere between caramel and cotton candy. because of the unprocessed sugars that are in there from the feedstock. And so it's not unpleasant at all. Disadvantages of the thing, has relatively poor environmental resistance. It doesn't stand up well long term to moisture or sunlight. It does degrade. Now it's not, I should say it's not a vampire. It's not going to disappear when you put it out in the sun or anything like that. But over a period of time, sun and rain will take their toll on PLA plastic, and it will delaminate or fall apart. And it has poor heat resistance. If you print something like this, and put it out in your hot car on a summer day, it will probably warp. It doesn't stand up to that very well. The whole PET family, PETG, PETG, PET itself, polyethylene terephthalate, if you ever see something with a recycling code of 1 on it, which would be a pop bottle or a water bottle, juice bottle, that kind of thing, PET, that's what it is. It's the most recycled plastic there is. It has the variant used for 3D printing is mostly PETG or PETG. It's a little less brittle and easier to print, and it has a somewhat lower melting point. The advantages over PLA are that it's less brittle. It's moderately resistant to moisture and UV, so if it's going to be something that sits outside, this is a good choice because it's inexpensive and fairly easy to print, and it's not going to fall apart. And disadvantages, a little harder to print, slightly more expensive, and a little less rigid if that's something you need. That's not always a disadvantage. ABS, you know ABS. ABS is what Lego blocks are made out of. So it's a hard, durable plastic. It's used for automotive parts, consumer electronics, piping. Your waste piping in your basement is probably ABS plastic. It's the black stuff. It's a little harder to print. Requires a heated bed and probably a chamber because of off-gassing. So you probably don't want to print it out in an open room. It's high strength. It's a relatively low-cost base material, high resistance to chemicals, moisture, and heat. So that's why it's used in automotives. It's used under the hood and can actually withstand the heat. Disadvantages, yeah, it's somewhat harder to print. Doesn't have necessarily really good UV resistance, and there is the outgassing during printing, which you need to take into consideration. ASA is one of my favorites. Acrylonitrile styrene acrylate. Wow. It's an engineered plastic. It was designed to address the limitations of ABS. It's used very commonly in outdoor furniture because it can lay there in the sun forever in the UV and the heat and the rain and everything else, and it doesn't hurt it. It's very, very durable plastic that way. Extreme weather resistance and good mechanical strength. Easier to print than ABS. It does require an enclosure and a heated print chamber. It outgasses styrene gas, which smells bad, will give you a headache, and is actually mildly toxic in high concentrations. So you do want ventilation or filtration if you're going to print this stuff. But it's a great plastic. I enjoy it a lot. TPU, I talked about TPU earlier. It's a flexible plastic. It's good for making things like handle grips and stuff like that. There's actually people printing their own footwear out of TPU now because it makes a nice squishy shoe. It's used in hoses and tubing and medical devices. It's biocompatible, which means that if you make it as a wristband on a watch or something, it's not going to make your wrist itch. It's not going to irritate. It can even be implanted. So it is a biocompatible plastic. Has some print challenges. It's stringing. It's very hydroscopic. It wants to pick up moisture from the air, and after that, it doesn't print very well. So you would have to dry it in order to print it again. And you probably do want a drying capability if you're going to print TPU with any regularity. But I used it for the gasket on the box I showed before. It worked great for that. It's a fantastic option. Nylon. Everybody knows what nylon is. It's an older plastic, been around forever, structural, resistant to abrasion, temperature, chemical, all that kind of stuff. Self-lubricating, makes really good hinges, bearings, slides, stuff like that. Doesn't gall. It's tough, it's reasonably priced. It is very hydroscopic again, so it has to be kept dry or dried before printing. It's somewhat UV sensitive, not really bad, and it is challenging to print. It's probably not the first one you want to try, but after you have a little practice, it's certainly approachable to us mere mortals. I want to talk about polypropylene. Polypropylene is, you'll see that in recycling code 5. The most common place you'll see that is those big plastic storage bins you have. That's polypropylene. And so it's a flexible plastic. It's very durable, resists chemicals. It can be steam sterilized, high breakdown voltage. So really nice for electrical stuff. And it's semi-transparent, lightweight. It is flexible. They make live hinges out of it so that you just print the hinge and it just flexes. And it's a common plastic for that. It can be a little challenging to print. It's hard to make it stick to the bed because it's a very slippery, greasy kind of a plastic, and it has to be printed fairly slowly. And then the last one I want to talk about is polycarbonate. You know it as probably Lexan. It's the windshield on your boat or your snowmobile or that kind of thing. It's a hard, transparent plastic. It's temperature resistant, moisture resistant. It's pretty UV resistant, actually. It's used for eyeglass lenses. Mine are polycarbonate. It's a little difficult to print. Poor bed adhesion. Most polycarbonate material for 3D printing is a copolymer. It's been blended with something else. If it hasn't been, if you end up with pure polycarbonate, it can be Satan's own filament to print. It's really challenging. But it makes a very, very hard, durable printed object. And then I want to talk really quickly about some of the add-ins. You can add fibers to the materials to make them, mainly to make them stronger in terms of tensile strength, also to make them much more rigid. And one of the cool things about making them more rigid is plastics that have a tendency to warp are easier to print if they have a fiber in them because it resists warping. And so it actually makes them a little easier to print. There's carbon fiber, which we all know about. There are potential electrical concerns. You probably don't want to make antenna insulators or coil forms out of carbon fiber because it's mildly conductive. Not a good thing. So if you want fiber in those kinds of things, it typically becomes glass fiber. It's a little heavier, but it actually improves the electrical characteristics of the plastic. So that's certainly a good thing. It's heavier. Then there's Kevlar, which is kind of uncommon. It doesn't really do anything to the electrical properties. It's heavier than carbon fiber, but lighter than glass fiber. It's hard to find, but it can be a good option if you happen to need that. I want to talk about exotics real quick. Things like PEK, PEKK, PEI. Those are very expensive. They're high temperature. They're used for aerospace and other strong engineering things. Some of these things are darn near as strong as cast aluminum. They're very, very durable. I want to talk a little bit about POM, which is known as Delrin. The only problem with Delrin is when it's printed, it can release formaldehyde gas. So again, it's not that you don't do it, it's that you're aware that it can do that. It's challenging to print because it doesn't want to stick to the print bed very well. PVC, polyvinyl chloride, it's the plastic pipe that we all use for antenna parts and everything else. You can't print that stuff. It takes a high temperature environment and it releases chlorine gas during printing. So again, probably not something you really want to do a lot. And conclusions, no perfect material. They all have different applications, very heavily dependent on what you want to do with them. And over time, you'll figure out which one's best for your particular situation, and that's what you'll do. So I think that's good stuff. I talked about this earlier. There are some future things where you can print ceramics, you can print glass, you can even print metal, not directly, but indirectly. AI is starting to invade the printer firmware space, so it will watch the actual print and adjust printer parameters to give you a better print over time. That's just evolving now, but that's going to become more of a thing, and it's going to make printing a whole lot easier from the mechanical perspective. Material science is progressing all the time. So you're going to get better stuff. One last thing I want to talk about. I know that oftentimes we get busy with other things and we never seem to get back to what we want to try for new stuff. And it's all too easy to say, well, I'll try that sometime if I ever get around to it. And so consequently, what I have done is I have solved that problem for you. I've printed a rather generous supply of round tuits, which I have right here, and I'm going to put the box out here. And I would very much appreciate if you would take one home with you.